Greetings, traveler. I'm the calculus cleric, and today we're working with differential equations. So the specific problem has three parts to it, A, B, and C. So I'll just read the general overview first. So it says the problem below shows a circuit consisting of a resistor of R ohms, a capacitor of C farads, and a battery of voltage V. When the circuit is completed, the amount of charge Qt in coulombs on the plates of the capacitor varies according to the differential equation T in seconds, and the differential equation is shown below. R multiplied by dq over dt plus 1 over c multiplied by q is equal to v, where r, c, and v are constants. So let's look over part A first. So they want us to solve for qt, assuming that q0 is equal to 0. So they want us to basically solve out this differential equation, and we can do this by taking the integrals of both sides to remove the dq over dt. So let's get started. I'm going to rewrite the differential equation and then isolate dq over dt by itself. And we're going to move the part of this equation that has a q over to the same side as a dq over dt. So multiply both sides by 1 over c by q. That will cancel out over here. Okay, and now we want to isolate the dq's and the dt's, and we want to split up the dq's and the dt's, so that way we only have dq with the q and dt with something else. So let me give myself some more room here. So we can multiply both sides by dt to get that. And then we take the integral of both sides. I'm going to start with the right side first, since it's much easier to do. Because we're taking the integral to the variable of t, there is no variable t here. So we just treat 1 over r like a constant, and we just put a t there. And I'm going to put an a. This is this is a constant. When we take the general integral, we normally put a plus c at the end, but because we're using c as a variable already, or it's a constant, but we're using c already, so we're just going to use a for that mystery variable that comes out when we take a general integral with no bounds. And then we have to perform a u substitution over here. So u is equal to v negative 1 over cq, and then du, the derivative of that, because we're taking this in terms of q, v is treated like a constant, so that's just 0, and then negative 1 over c dq, because 1 over c is also just a constant. And so rewriting this over there, oh right, and then we're going to have to isolate the dq by itself, so that way we can substitute it out. So negative c and du is what is going to replace the dq. Okay, so this is what it looks like right now. Next. And then we take the integral of this. Negative c is just treated as a constant. Ln of u, the absolute value of u, is equal to 1 over rt plus a, but we have to replace u with what we substituted out earlier. So I'll be replaced with v minus 1 over cq is equal to 1 over rt plus A. Now that's rather messy, but what they want us to do in the end is to find Q of t. So in all essence, we have to isolate Q by itself. And then from here, we can just use algebra to solve this out, although this algebra will be somewhat difficult. And then 1 over RT plus A, I divided both sides by negative C. And I just wrote it out prematurely. And if you divide both sides by negative C, the one on the left will cancel out and leaves only the one on the right. And I'm just going to rewrite that. And we're just going to leave A as A instead of A divided by negative C because A is a mystery constant. And if you divide a mystery constant by a constant, you can just absorb that into the original mystery constant because it's still a mystery. It's not like anything has changed because that just tells us our starting value. And then to cancel out the natural log, we'll have to take both sides to the e to the exponent. It's 1 CR. It's easier to write it out than explain it in words. And then we can move the a to the front of the e. Okay. And then from here, then we have to just start isolating the t. So we subtract v from both sides. So that cancels out. 1 negative 1 over c. Q is equal to ae to the negative 1 over crt minus v. And then we multiply both sides by negative c, which leaves us with q is equal to negative c ae to the negative 1 over crt plus cv because the negatives cancel and become a positive symbol. Negative by negative is positive. And from here, we can use the information they gave us that q of 0 is equal to 0, and we can plug that right in. So 0, and it says that q of t is what we're solving for, so we have to replace our t variable with the 0. And that will get rid of this whole mass of variables over there because 0 multiplied by anything is 0. And then from here, replace e to the 0 is just 1, so negative ca plus cv. So from here, we can use this to solve what a is, our mystery constant. So add both sides, add ca to both sides, ca equals cv, divide both sides by c, and you have a is equal to v. Okay, so that's nice. Let's rewrite this out one more time. We're just going to have to copy this over, but then replace the a with a v. And so that is our final solution for part A. And part B, so we're going to have to take the limit of that equation. Q is equal to C V e to the negative 1 over CRT plus CV. Okay, so they want us to take the limit when t approaches infinity of this equation, basically. And they want us to prove that the said limit is CV. Okay, so because this is taken to a negative exponent, we can reciprocate this part of the equation to get us a positive exponent, and it makes it a lot easier when we work with the limit when t approaches infinity. N is a habit. Do not copy that. So it's supposed to be when t approaches infinity, not when n approaches infinity. Okay, so when we take this out to infinity, you notice the whole bottom will become infinity, and 1 over infinity, as we know it, is 0. So it just leaves us with CV. So indeed, when we take the limit as t approaches infinity, we will get CV. So that does work out. That is true. So now we have to do part C. Show that the capacitor charges to approximately 63% of its final value CV after a time period of length tau is equal to RC, where tau is called the time constant of the capacitor. Now, that's a lot of jargon, and basically what it's telling us is they want us to find when Q of t is equal to somewhere around 0.63. Let me replace that with an approximate sign. Because the capacitor charge is QT over here, the amount of charge QT, and 63%, well, that's just a decimal representing 0.63. And tau is equal to RC. Well, T is the time constant of the capacitor, but it says length, time period. So we know that tau is actually telling us our time. So our t variable that we have up there is going to be our c. And now we just plug this back into the equation we found in part A. I'm going to rewrite out the equation one more time. And then we plug in RC into our t. We can't plug in 0.63 yet because that's what we're trying to find. And RC can be written as CR just so we can see how these two cancel out to 1. And that gives us Q is equal to negative CV of E to the negative 1 plus CV. And because there are CVs on both sides, then we can factor out a CV. Negative E to the negative 1 plus 1. There was one thing that I forgot to mention. It says that 63% of its final value CV. So we can leave CV as it is. We don't have to worry about what value CV comes out to because they're mystery constants. We wouldn't be able to figure them out anyways. So we just simply need to know what this comes out to in decimals. So you would use a calculator for this because there's no way to do it by hand. At least not a way that I know of. Add 1 plus negative e to the negative 1, 0.6321205588, and so on and so on. So this is approximately 0.63. So yeah, we can say that when the time is equal to RC, then the capacitor does charge to around 63%. And so that's it for part C.